Hello there, and welcome to Mysteries of Earth. The Lonely Voyage. Space is silence. Space is darkness. Space is vast beyond imagination. A realm so immense that even light itself seems to crawl across its emptiness. From our vantage point, on a tiny blue planet, it is almost impossible to comprehend the sheer scale of the universe that surrounds us. The stars we see at night, each a blazing sun in its own right, are not close neighbors. They are distant beacons, scattered across incomprehensible gulfs of emptiness. Between them lies more nothing than we can ever truly experience. A yawning chasm of vacuum that stretches for light years, billions of kilometers, where even a spacecraft traveling at tens of thousands of kilometers per hour would take centuries to traverse. Yet, despite this isolation, humanity has dared to venture outward. Among our most remarkable emissaries is the Voyager spacecraft, launched in 1977. Voyager 1 and 2 were designed to explore the outer planets, but their journey did not end there. After completing their planetary missions, they continued into interstellar space, becoming the first human-made objects to leave the heliosphere, the protective bubble of solar wind that surrounds our sun. Today, Voyager 1 drifts silently through the cold darkness beyond the planets, more than 23 billion kilometers from Earth, a distance so vast that conventional human scales can no longer measure it. Voyager 2 follows a similar path, carrying with it the golden records, a message in a bottle for any extraterrestrial civilization that might one day encounter it. Consider that for a moment. Our most distant explorers are tiny specks of metal, carrying the essence of human culture, gliding alone through a void that stretches wider than our minds can easily grasp. They are on a voyage without witnesses, moving through a cosmic sea where no sound travels, no breeze blows, and no landmarks exist. Each second of their journey is a reminder of the immensity of space, the emptiness between stars, and the fragile significance of our own existence. The distances involved are staggering. The nearest star system to our sun, Alpha Centauri, lies more than 4 light-years away. In kilometers, that is over 40 trillion. To put that into perspective, if the sun were the size of a basketball, Alpha Centauri would be more than 1,000 kilometers away, farther than any terrestrial journey we have ever made. Yet even this is just the beginning. Our Milky Way galaxy, a sprawling city of stars, gas, and dark matter, extends more than 100,000 light-years across, and it contains hundreds of billions of stars. Beyond it, neighboring galaxies like Andromeda lie millions of light-years distant, while the edge of the observable universe stretches some 46 billion light-years in every direction. In the grand scheme, Voyager's journey is a minuscule ripple in a cosmic ocean, yet it symbolizes something far greater: our urge to reach outward, to understand the ungraspable, and to explore what lies beyond our immediate experience. But this journey into emptiness also invites reflection on time. On the scale of human life, decades or centuries seem long, yet in galactic terms, they are almost instantaneous. Voyager has been traveling for more than 4 decades, yet that is barely a heartbeat in the life of a galaxy. Our solar system itself orbits the Milky Way at an average speed of about 828,000 kilometers per hour, completing one revolution around the galactic center approximately every 225 to 250 million years. That means that since the dinosaurs walked the Earth, our solar system has completed only a single orbit. a journey that Voyager could never hope to emulate in its lifetime. Biological time, the fleeting moments of life as we experience it, is dwarfed by the vast, slow currents of galactic motion. Even as Voyager drifts further into the interstellar void, it remains bound by the gravitational currents of our galaxy. Our solar system is not stationary. It is a passenger on a grand cosmic river, carried along by the unseen forces of the Milky Way's massive spiral arms, dark matter halo, and central gravitational anchor. Every planet, every asteroid, every speck of dust in our system participates in this slow, inexorable dance. And yet, to Voyager, these movements are imperceptible. From its perspective, it is alone in a near-perfect void, hurtling forward without any visible frame of reference. A solitary Voyager through emptiness. We cannot witness this journey directly. Even our most powerful telescopes, capable of resolving galaxies billions of light-years away, cannot track an object as small as Voyager in real time. Its passage is known only through careful calculations, radio signals that take hours to reach us, and the steady tick of instruments engineered for longevity in a harsh environment. In a sense, Voyager is a bridge between scales. It is both a human artifact and a cosmic traveler, connecting the brevity of our existence to the eternity of interstellar space. Its journey forces us to confront a humbling truth. The universe is not built for us, nor does it operate on the scales we naturally comprehend. Our lives, our histories, and even our civilizations are but fleeting phenomena in a cosmos that endures for billions of years beyond our presence. As we consider the void through which Voyager travels, we begin to understand how isolation and perspective shape our perception of the universe. Each star we see is not merely a point of light. It is a distant sun with its own system of planets, its own history of formation, evolution, and destruction. Each gap between stars is not empty in an absolute sense, but filled with tenuous hydrogen clouds, cosmic rays, and dark matter, invisible currents that shape the structure of the galaxy itself. Space is simultaneously empty and full, silent yet seething with energy, a paradox that challenges the limits of human imagination. The interstellar medium, though sparse, is not nothing. It contains a ghostly presence, atomic and molecular clouds, tenuous plasma, and magnetic fields that stretch for light years. These invisible threads can influence star formation, bend the trajectories of particles, and even redirect the paths of spacecraft traveling through their influence. Voyager passes through these subtle landscapes without notice, but the medium itself is a living record of the galaxy's slow evolution, holding secrets about the birth of stars and the distribution of matter across millions of light years. And then there is the question of scale. Voyager travels at roughly 17 kilometers per second, a remarkable speed by human standards. Yet at this velocity, it would still take more than 70,000 years to reach the nearest star. When measured against galactic scales, even this extraordinary journey is a crawl. The emptiness of space is absolute in its enormity. The distances between stars are so vast that they challenge our intuition and leave us grasping for analogies that fall short. A single light year is over 9 trillion kilometers, a distance our minds struggle to picture. Crossing even one such distance at Voyager's speed is akin to walking across an entire continent for millennia without pause. Yet in this loneliness, there is beauty. There is wonder in the thought that humanity has cast its voice into the cosmos, knowing it may never be heard. Voyager carries not just instruments and metal, but also the golden records, the sounds of our world, music, greetings, and images meant to tell the story of life on Earth. In a universe so vast that civilizations may never counter one another, these small tokens are our gesture of existence, a quiet statement that we were here, that we observed, that we dared to reach beyond our cradle. And perhaps therein lies the deeper lesson of the lonely voyage. Our significance is not measured in distance traveled or stars reached, but in the act of observation itself. To understand our place in the cosmos, we must recognize the immensity of what surrounds us and our relative smallness within it. Biological time, the fleeting scale of a single human life, is dwarfed by the orbits of stars, the rotations of galaxies, and the expansion of the universe itself. Yet our curiosity, our desire to explore, persists despite the gulf of space and time. Voyager exemplifies this duality, fragile, finite, yet endlessly reaching. As we ponder the empty stretches that separate us from the stars, we are reminded that our perspective is inherently limited. We cannot step outside our galaxy to observe it in full. We cannot witness the motions of stars over hundreds of millions of years firsthand. But through ingenuity, instruments, and imagination, we can extend our senses across space and time, piecing together a vision of the universe that approaches truth. The loneliness of space becomes a lens through which we examine our place in the grand cosmic story. And as Voyager continues its silent trek into interstellar darkness, it carries with it the anticipation of what lies ahead. Beyond the emptiness of our solar neighborhood, the Milky Way unfolds as a colossal city of stars, gas, and dust, spinning through space. It is here that our journey truly begins, not in the silent void, but within the swirling, living architecture of our own galaxy. The lonely voyage of a single spacecraft reminds us of the vastness to come, the complexity we have yet to encounter, and the profound mysteries that await when we turn our gaze inward to explore the cosmic home we call the Milky Way. Soon, we will leave the emptiness of interstellar space behind and step into the teeming streets of our galactic home, where stars are born and die in cycles that stretch over billions of years. From Voyager's lonely trek to the heart of our galaxy, the journey continues, revealing that even in the vast solitude of space, the cosmos is alive, dynamic, and endlessly fascinating. Stars beyond counting. Look up on a clear night, and the sky seems infinite. Each pinprick of light appears delicate and fragile, suspended in a vast, dark canvas. Yet behind that delicate glow lies a staggering truth. Our Milky Way is home to an estimated 400 billion stars, billions upon billions of luminous suns, each a raging sphere of plasma, spinning, fusing, and radiating energy across unimaginable distances. To even begin to comprehend such numbers, we must step back from human scales and think in terms of cosmic time and space. Consider this. If we attempted to count one star per second without pause, it would take over 12,000 years to tally them all. And even then, we would barely scratch the surface, for stars are born and die on scales that make millennia seem ephemeral. Our galaxy is not a static collection of stars frozen in time. It is a living, dynamic system, constantly reshaped by creation, destruction, and motion. Among these billions of stars exists a dizzying diversity. Stars vary in size, color, and lifespan. Some are giants, tens, or even hundreds of times the mass of our sun, burning furiously and living fast lives that end in spectacular supernova explosions. Others are diminutive red dwarfs, small, dim, and unassuming, yet capable of shining steadily for tens or even hundreds of billions of years. Their longevity far exceeds the current age of the universe, allowing them to outlive entire generations of galaxies. The colors of stars reveal their temperature and composition. Blue stars blaze with heat, often exceeding 20,000 degrees Celsius on their surfaces. Yellow stars, like our Sun, emit a steadier, more moderate glow. Red stars are cooler, yet no less significant. They provide a stable environment where planets could potentially harbor life for billions of years. Observing these colors is like reading the cosmic biography of a star. Each we a chapter in a tale that began in a cloud of primordial gas. Many stars are not solitary travelers. Binary systems where two stars orbit a common center of mass are common throughout the Milky Way. In some cases, these stars dance so closely that their atmospheres intermingle, exchanging matter in a gravitational embrace. Clusters, too, abound, dense pockets of stars born from the same molecular cloud, bound together by gravity and tracing shared orbits across the galaxy. Globular clusters, ancient and tightly packed, contain hundreds of thousands of stars, relics of an era when the Milky Way was young. Open clusters, more loosely bound, are often nurseries of new stars, where cosmic infants twinkle alongside their siblings in brilliant constellations. Amid this stellar abundance, we begin to understand the conditions for life. Not every star can host habitable worlds, yet some offer the perfect balance. Around certain stars exists a Goldilocks zone, a region neither too hot nor too cold, where liquid water can persist on a planetary surface. Here, the ingredients of life, carbon, oxygen, nitrogen, and water, might assemble in intricate self-replicating patterns. The very existence of billions of stars means that potential cradles for life could be countless. Each solar system is a laboratory, each planet a canvas, where chemistry dances over eons. And yet, the question remains, how many of these worlds ever nurture life? How many remain silent, dark, or inhospitable? Even within our own solar system, we glimpse this diversity. Our Sun, a middle-aged yellow star, supports a planetary system of vast contrast, from scorching Mercury to icy Neptune, from molten early Earth to the frozen moons of Jupiter and Saturn. Scale this up across the Milky Way, and the possibilities become dizzying. Some stars may host worlds with multiple suns in their sky, casting complex shadows across alien landscapes. Others may be surrounded by planets so close that years are measured in days, their surfaces scorched by relentless solar radiation. In this cosmic theater, Earth is but one stage among billions, one story among untold millions. And yet, despite this staggering diversity, stars share a rhythm dictated by time, cosmic time, immense and unyielding. Stars are born from clouds of gas and dust, coalescing under the slow pull of gravity. They shine, fuse hydrogen into helium, and evolve, moving through life stages determined by their mass. Massive stars live fast and die young, sometimes in violent supernovae that scatter their enriched material across space. Smaller stars live long and steady, quietly feeding the interstellar medium with gentle winds. Each generation of stars enriches the galaxy with heavier elements, the building blocks of planets, rocks, and, eventually, life itself. Here, we confront a profound contrast between cosmic time and human time. While stars live for millions or billions of years, humans exist for mere decades. Civilizations rise and fall like ephemeral sparks, barely registering on the scale of galactic history. We are observers, fleeting witnesses to a drama that unfolds over scales that dwarf our comprehension. Yet our curiosity, our capacity to study, understand, and reflect, allows us to connect our brief lives to the lifetimes of stars, to glimpse the patterns that govern their existence, and to imagine what world may orbit unseen suns across the galaxy. Clusters and streams of stars reveal the past history of our Milky Way. The galactic halo, a spherical region surrounding the central disk, contains stars that may have originated in smaller satellite galaxies, cannibalized and absorbed over billions of years. Each star carries a chemical fingerprint, a record of its birthplace and ancestry. In studying these stellar populations, astronomers unravel the Milky Way's formation history, tracing mergers, migrations, and disruptions that have shaped our galaxy into the vast structure we observe today. Within this teeming galaxy, our sun resides in a relatively quiet neighborhood, part of the thin disk of the Milky Way. Here, star formation continues at a moderate pace. Nebulae glow with the light of newborn stars, their gases slowly coalescing into planetary systems. Supernovae punctuate the landscape with bursts of energy that propagate across light years, compressing clouds and triggering new generations of stellar birth. It is a dynamic environment, yet one that unfolds on timescales far longer than any human lifetime. The diversity of stars also reminds us of the fragility of life. Planets orbiting massive, short-lived stars may never have time to develop complexity before their suns explode. Worlds around volatile stars may be bathed in radiation, sterilizing surfaces that could otherwise nurture life. And yet, the long, steady lives of smaller stars offer the promise of stability, a window of time where life could emerge, evolve, and perhaps even look up at the night sky and wonder, as we do, about the countless other suns above. In contemplating the Milky Way's billions of stars, we are drawn to our own smallness, but also to our capacity for imagination. Each star is a sun with its own story, a potential cradle of life, a witness to the unfolding of cosmic history. We are passengers in a galaxy filled with brilliance, yet we can never see all of it at once. From Earth, we glimpse fragments of this vast stellar population, patterns in the night sky, glimmers of distant clusters, the faint halo of ancient stars. Each observation is a piece of a puzzle, each measurement a step toward understanding the larger whole. And so, we begin to see the galaxy as more than a collection of stars. It is a cosmic city, a vast network of stellar populations, interstellar clouds, magnetic fields, and dark matter, all woven together in a dynamic, evolving structure. Our sun is but one citizen in this grand city, Earth a tiny apartment in a sprawling metropolis of light and energy. The stars, both near and far, are neighbors in a neighborhood that stretches for 100,000 light years, yet each is unique, with its own history, environment, and potential to harbor life. This realization inevitably leads to profound questions. How many other worlds are out there, circling suns like ours, waiting for life to take root? How many civilizations have arisen, only to vanish without leaving a trace? Are we alone? Or are we part of a galaxy teeming with unseen observers? The Milky Way invites these questions because it reminds us that on cosmic scales, Human existence is brief, but observation and understanding can stretch across time, linking our fleeting presence to the slow unfolding of stars. As we gaze at the night sky, we are simultaneously humbled and inspired. We are small, yet capable of insight, transient, yet able to perceive permanence, brief, yet able to contemplate eternity. The Milky Way's 400 billion stars are both a backdrop and a stage, setting the scene for the story of life, the story of galaxies, and the story of the cosmos itself. And as we explore these billions of suns, we begin to understand that our journey is not just through space, but through time. A journey that connects the brief history of Earth and humanity to the ancient, ongoing evolution of the stars. Every star is a chapter, every cluster a volume, and every spiral arm a library of cosmic history. To study them is to read the story of the universe, written in light and motion, in fusion and gravity, in creation and destruction. And as we learn more about these stars, we gain a perspective that transcends human scales, one that situates us within the rhythm of galactic life, between the birth of stars and the slow decay of ancient suns. In the next chapter, we will move beyond the stars themselves and explore the galactic neighborhoods they inhabit. From clusters and streams to bars and spiral arms, the Milky Way is not merely a collection of stars, but a structured living system, shaped by forces both visible and unseen. The patterns we observe reveal the hidden architecture of our galaxy, a framework that guides the motion of stars and defines the cosmic city we call home, the galactic clock. Look up at the night sky, and the stars may appear fixed, eternal, a silent backdrop against which human history unfolds. But appearances are deceiving. Every star, including our sun, is in constant motion, tracing an orbit around the center of our galaxy. The Milky Way is not static. It is a vast, rotating system, a cosmic carousel of stars, gas, and dark matter, all moving in concert according to the invisible laws of gravity. Our sun, seemingly so steadfast in its place, completes a full orbit around the galactic center, roughly once every 225 to 250 million years. Astronomers call this period a cosmic year, the time it takes for our solar system to make one complete journey around the Milky Way. To put this into perspective, the dinosaurs appeared about one cosmic year ago. Modern humans, by contrast, have existed for barely a fraction of a single rotation. In the grand scheme of galactic time, human history is a fleeting heartbeat, an instant in a rhythm that has been unfolding for billions of years. The motion of stars within the Milky Way is not uniform. Stars closer to the galactic center orbit faster, while those on the outer edges drift more slowly, a phenomenon known as differential rotation. This variation in orbital speed stretches the spiral arms into the sweeping curves we observe in images of our galaxy. Like brushstrokes on a cosmic canvas, these arms are patterns of density waves, not rigid structures, guiding the motion of stars, gas clouds, and nascent planetary systems. Our sun itself is not a passive traveler. It oscillates up and down through the galactic plane, moving in a gentle bobbing motion like a ship on slow cosmic waves. Roughly every 30 to 35 million years, the solar system passes through the dense midplane of the Milky Way, where stars, gas, and dust are more concentrated. These crossings may have influenced Earth, is history, potentially correlating with episodes of increased comet impacts or shifts in climate. Even in our apparent isolation, the galaxy exerts its influence, subtly shaping the conditions for life on our small blue planet. As the sun and stars orbit, the familiar constellations we know from Earth are not fixed either. The patterns of Orion, Ursa Major, and Cassiopeia are temporary alignments, fleeting arrangements that exist only within a narrow window of time. Thousands of years ago, these constellations looked different. Thousands of years from now, they will be unrecognizable. The night sky, it turns out, is as much a time machine as it is a map, revealing the motion of stars over eons. Each point of light carries information not just about space, but about time. The story of its journey through the galaxy, the forces that guide it, and the cosmic rhythms that govern its motion. The galactic center, hidden from direct view by dense clouds of dust and gas, exerts a gravitational pull that organizes the orbits of billions of stars. At the very heart lies a supermassive black hole, millions of times the mass of our Sun, anchoring the Milky Way and orchestrating the motion of its stellar citizens. Around this central anchor, stars move in elliptical orbits, their speeds dictated by the balance between gravity and momentum. Some stars, known as hypervelocity stars, are flung outward by gravitational interactions, escaping the galaxy entirely. Others move in tight, rapid orbits near the galactic core, completing a revolution in mere millions of years. The concept of a cosmic year allows us to relate galactic motion to Earth's own history. One rotation of the Sun around the Milky Way spans the rise and fall of entire species. 14 cosmic years have passed since the formation of our solar system. The Cambrian explosion, the rise of dinosaurs, the formation of the Himalayas, all occurred as the Sun traced its orbit around the galactic center. In this context, human civilization is almost imperceptible, yet it exists precisely because of the stability afforded by our orbit, our gentle passage through a relatively calm region of the galaxy. Beyond the Sun, other stars trace their own intricate paths. Some move in clusters, bound tightly by gravity, while others are loners, drifting through space on solitary journeys. Stellar encounters, though rare on human timescales, are inevitable over cosmic millions of years. A passing star may perturb distant comets in the Oort cloud, sending them careening toward the inner solar system. Galactic tides, created by the combined gravity of billions of stars, and dark matter, subtly shape the structure of the Milky Way, bending stellar orbits and influencing the evolution of the spiral arms. The spiral arms themselves are not fixed structures, but waves of density, regions where stars and gas crowd together temporarily. As stars move through these arms, they experience changes in their environment. Gas clouds are compressed, triggering new rounds of star formation. Older stars drift away from the arms, becoming part of the more diffuse galactic disk. This cycle repeats over hundreds of millions of years, a dynamic, ever-changing rhythm that defines the architecture of our galaxy. Even on smaller scales, the Milky Way behaves like a clockwork mechanism, each component influencing another. The Sun's passage through the galactic plane may affect the influx of cosmic rays reaching Earth. Gravitational interactions with nearby stars or satellite galaxies can induce waves in the disk, altering the motion of gas clouds and influencing star formation. The galaxy's magnetic field, a subtle but pervasive force, threads through the spiral arms, guiding charged particles and shaping the interstellar medium. All of these components contribute to a grand, interlocking system, a cosmic clock, in which time is measured not in seconds or years, but in the rotations of stars and the oscillations of galactic structures. Constellations, once thought to be eternal, are reminders of our fleeting perspective. As the sun moves along its orbit, the stars behind it shift slowly, their positions changing over tens of thousands of years. Orion's belt, the Pleiades, the Big Dipper. These are temporary snapshots in an ongoing celestial ballet. Civilizations past and future will see different skies, yet the underlying clockwork of the galaxy continues, indifferent to human observation. This motion also gives rise to stellar streams, trails of stars torn from smaller galaxies consumed by the Milky Way. As these stars orbit the galactic center, they trace arcs and ribbons that slowly wrap around the galaxy. These streams, remnants of galactic cannibalism, are a visible record of the Milky Way's history, evidence that our galaxy grows not only by forming new stars, but also by devouring smaller neighbors. They are cosmic footprints, a reminder that motion and time are inseparable on the galactic scale. In contemplating the galactic clock, we confront the interplay between stability and change. The sun's orbit provides a relatively stable environment for life on Earth, yet nothing in the galaxy is permanent. Spiral arms wind and unwind. Stars drift from one region to another, and the positions of constellations evolve. The galaxy is simultaneously a sanctuary and a dynamic force, a vast machine that operates over timescales far beyond human comprehension. Our understanding of the Milky Way's motion has grown through careful observation and sophisticated computer modeling. Satellites such as Gaia have mapped the positions and velocities of over 1 billion stars, revealing the subtle motions of our galaxy in unprecedented detail. From these observations, astronomers have reconstructed the sun's path, the oscillations of the galactic disk, and the intricate patterns of stellar streams. Each measurement brings us closer to understanding the Milky Way, not as a static backdrop, but as a dynamic system, a clockwork of unimaginable complexity. And yet, despite all we know, the galaxy retains its mystery. Even the motions we can measure are influenced by invisible forces. Dark matter, which outweighs visible matter by a factor of 5, provides the gravitational scaffolding that holds the Milky Way together. Without it, the galaxy's rotation would tear it apart. The spiral arms, the stellar disk, the galactic halo, all are shaped by an unseen hand, reminding us that the motions we observe are only part of a larger hidden reality. As we trace the sun's journey around the galactic center, we begin to see time on a scale that is almost incomprehensible. One orbit spans the rise and fall of continents, the evolution of species, the formation of mountains and oceans. 4 or 5 orbits have passed since complex life emerged on Earth. Every cosmic year is a silent chronicle of Hangi, an era-long tick of the galactic clock. And yet, even as the sun moves along its orbit, we remain inside the galaxy, unable to step outside and observe the full motion. We see only snapshots, pieces of a vast ongoing movement, glimpses of the grand mechanism that governs the lives of stars. The galactic clock teaches us perspective. Human lifetimes are brief, civilizations are transient, yet the universe continues in its steady rhythm. Stars move, spiral arms rotate, galaxies orbit, and cosmic time marches on, indifferent to the concerns of fleeting observers. And within this rhythm, Earth exists as a small stage where life has emerged, flourished, and contemplated the very forces that shape its environment. The next step in our journey will take us from the motions of individual stars to the larger structures that orchestrate them. From spiral arms and bars to the Milky Way's halo, we will explore the architecture of our galaxy, the invisible scaffolding that guides stars, shapes planetary systems, and defines the cosmic environment in which our Sun and Earth reside. The galactic clock is not merely a measure of time. It is a framework upon which the history of our galaxy and the story of life within it unfolds. The invisible heart. At the heart of the Milky Way lies a presence that defies ordinary perception. Hidden behind dense clouds of interstellar dust and glowing gas, it is a void of unimaginable density, a supermassive black hole, known to astronomers as Sagittarius A. Invisible to the naked eye, undetectable through ordinary telescopes, it nonetheless exerts a gravitational influence that orchestrates the motion of billions of stars and shapes the very structure of our galaxy. To contemplate Sagittarius A is to confront a region where space and time themselves are stretched, twisted, and distorted. This black hole contains roughly 4 million times the mass of our Sun, yet it occupies a region scarcely larger than the orbit of Mercury. To imagine this is to envision a sun-sized sphere capable of holding the gravitational equivalent of millions of suns. Its gravitational pull dominates the central parsecs of the Milky Way, dictating the paths of nearby stars, gas clouds, and even exotic phenomena such as neutron stars and stellar mass black holes. Close to this invisible heart, orbital speeds reach staggering velocities, with stars whipping around in mere decades, moving at thousands of kilometers per second. A single misstep or gravitational encounter could fling a star into oblivion, either into the black hole itself or outward into the wider galaxy as a hypervelocity star. Time behaves differently near this cosmic anchor. General relativity predicts that time dilates in strong gravitational fields, slowing relative to more distant observers. Near Sagittarius A, seconds stretch into minutes, minutes into hours. A journey toward the black hole is a journey into warped reality, a region where cause and effect follow unfamiliar rules. Matter spiraling inward experiences frame, dragging, a twisting of space-time caused by the black hole's rotation. This is not mere theory. It has observable consequences. Gas and dust caught in this gravitational whirl are forced into spiraling accretion disks, heated to millions of degrees, glowing fiercely in X-ray and infrared light before vanishing beyond the event horizon. The galactic core is a region of extremes. Stars crowd together, separated by mere fractions of a light year, a chaotic dance governed by gravity. Collisions, close encounters, and gravitational perturbations are commonplace. Some stars orbit in coherent clusters, their paths forming temporary patterns that survive for millions of years before dissolving into randomness. Others wander too close to the black hole, stretching into elongated streams under tidal forces so strong they can rip a star apart in dramatic stellar flares. Amid this chaos, Sagittarius A is a silent anchor. Without a central gravitational anchor, the Milky Way would lack coherence. Spiral arms would unravel, orbits would destabilize, and the galaxy might slowly scatter into space. The black hole is both a destroyer and a preserver, a paradoxical heart that consumes but also maintains the rhythm and order of the galaxy. Each feeding event, each captured star, contributes to its growth, yet the black hole's gravitational pull also organizes stellar populations across tens of thousands of light years. It is a cosmic choreographer, orchestrating motions that span millions of years and countless generations of stars. Observing the galactic center is a challenge. Interstellar dust obscures visible light, hiding Sagittarius A from ordinary telescopes. Infrared and radio observations are required to pierce the veil, revealing a region alive with activity. Clouds of gas swirl violently, compressed by gravitational tides into glowing filaments. Stars orbit in dizzying arcs, some traveling nearly at the speed of light. Occasionally, the black hole awakens, accreting matter in sudden bursts of energy that outshine entire star clusters. These feeding events release X-rays and gamma rays, illuminating the galactic core for brief periods, a fleeting display in a region otherwise dominated by darkness. Despite the apparent violence, the galactic center is surprisingly structured. Observations reveal rings of young stars orbiting Sagittarius A in relatively ordered planes, hinting at bursts of star formation triggered by gas flows toward the core. Massive clouds of molecular gas, compressed by gravitational tides and supernova shocks, form temporary nurseries where new stars are born. Yet, survival here is not guaranteed. The radiation environment is intense. High-energy photons bombard nascent stars and planets, stripping atmospheres and altering chemical compositions. To live near the galaxy's heart is to exist in a region of constant risk and transformation. The black hole's influence extends beyond the immediate core. Its gravity affects the orbits of stars tens of thousands of light-years away. It interacts with the galactic bar, a massive elongated structure of stars that channels gas toward the center, fueling both star formation and black hole growth. This interplay shapes the dynamic structure of the Milky Way, linking the unseen forces at the core to the grand architecture of spiral arms, disks, and halos. Yet Sagittarius A is largely a patient presence. Despite its destructize V potential, it grows slowly, feasting intermittently. It is a reminder that cosmic time is measured differently than human time. While we obsess over years and decades, the black hole operates over millions and billions of years. Stars that appear stable in our lifetimes are transient in its gaze, their lives insignificant compared to the slow accumulation of mass at the galaxy's core. The study of Sagittarius A has advanced dramatically in recent decades. Observations using adaptive optics, radio interferometry, and space-based telescopes have allowed astronomers to track individual stars orbiting the black hole. The paths of these stars, bending in perfect ellipses, provide direct evidence of the black hole's immense mass. One star, known as S2, completes an orbit around Sagittarius A every 16 years, reaching speeds of over 5,000 kilometers per second at its closest approach. By observing its motion, scientists have confirmed predictions of Einstein's general relativity, witnessing firsthand the warping of space-time around a supermassive black hole. Sagittarius A also offers clues to galactic evolution. Supermassive black holes are not unique to the Milky Way. Nearly every massive galaxy hosts one at its center. The interplay between black holes and their host galaxies shapes star formation, regulates gas inflow, and influences the growth of spiral arms and bulges. In this sense, our galaxy's invisible heart is both typical and extraordinary, a common feature across the universe, yet a defining influence on the environment that makes life on Earth possible. The galactic core reminds us of contrast and balance. It is a place of immense violence and extreme conditions, yet it sustains order over cosmic distances. Stars are torn apart, yet new stars are born. Matter is consumed, yet the galaxy itself grows and stabilizes. Time is distorted, Yet the overall rotation of the Milky Way continues predictably. In this paradox lies a profound lesson: that destruction and creation, chaos and structure, can coexist on unimaginable scales. Even the light from this hidden region carries stories across space. Photons emitted from the inner parsecs of the galaxy take tens of thousands of years to reach us, meaning we see the galactic center as it existed long before modern humans walked the Earth. Every image, every measurement, is a glimpse into a past that is simultaneously distant in space and time, a window into processes that have shaped the Milky Way for billions of years. Sagittarius A also serves as a cosmic laboratory for extremes of physics. Within its sphere of influence, the laws of gravity, thermodynamics, and quantum mechanics collide in ways that are impossible to replicate on Earth. Gas clouds are heated to millions of degrees. Magnetic fields are stretched and twisted into unimaginable configurations. Jets of high-energy particles are sometimes ejected into the surrounding halo. By studying these phenomena, we gain insight not only into our galaxy, but into the fundamental rules governing the universe itself. Ultimately, the supermassive black hole at the Milky Way's heart is both invisible and omnipresent. We cannot see it directly, yet its influence defines the galaxy's structure and evolution. It anchors billions of stars, governs the spiral arms, and maintains the rhythm of stellar motion. Without it, the Milky Way would unravel into disorder. It is a reminder that the most powerful forces in the universe are of 10 unseen, their presence inferred through motion, light, and gravity. As we step back from the galactic center, we begin to appreciate the Milky Way as a complex, interconnected system. Stars orbit in harmony and chaos. Spiral arms rotate like clockwork, and an invisible black hole at the core quietly shapes the fate of the galaxy. Our sun and solar system trace their paths through this immense structure, riding the gravitational currents dictated by Sagittarius A and the surrounding mass of stars and dark matter. The invisible heart of the galaxy hints at the next stage of our journey. The broader structure of the Milky Way, from its spiral arms and central bar to the halo and satellite galaxies that encircle it. Understanding the black hole is a glimpse into the forces that shape the Milky Way on every scale. And yet, this is only part of the story. Beyond the chaos and gravity of the core lies a galaxy that stretches across hundreds of thousands of light years. A city of stars, shaped by both seen and unseen forces, mapping from within. Imagine trying to map a vast forest while standing deep within its darkest groves, unable to see the edges of the canopy or the farthest tree. This is the challenge astronomers face when attempting to chart our own galaxy, the Milky Way. Unlike distant galaxies, which can be photographed from the outside in a single sweep, our cosmic home surrounds us. Every observation is made from within, a position both intimate and confounding. We are residents and explorers simultaneously, trying to decipher the grand design while living inside it. Our galaxy, spanning over 100,000 light years from edge to edge, is not empty space punctuated by stars. It is a dynamic, layered environment filled with dust, gas, and turbulent interstellar clouds that obscure our vision. In visible light, these clouds form a dense, patchy curtain, blocking our view of the galactic center and distant regions of the disk. Entire sections of the Milky Way appear dark to telescopes operating in ordinary wavelengths, making direct observation of its structure impossible without ingenuity and specialized tools. For centuries, humanity could only speculate about the Milky Way's true shape. Early astronomers sketched spiral-like patterns based on star counts and nebula. Yet these approximations were limited. The very stars we used as markers are unevenly distributed. Some regions teem with clusters, while others are nearly empty. Dust lanes, invisible to the naked eye, twist through the disk, blotting out thousands of stars and creating the illusion of gaps and voids. Our vantage point within the galactic plane is like trying to draw a map of a city while standing in its subway tunnels. Each view is incomplete, each measurement a fragment of a larger hidden reality. The advent of infrared astronomy began to lift this cosmic veil. Infrared light penetrates dust far more effectively to hand-visible wavelengths, revealing regions long concealed from view. The Spitzer Space Telescope, launched in 2003, transformed our understanding of the Milky Way's inner regions. For the first time, astronomers could see the dense stellar population near the galactic center, tracing patterns of stars in a region that had appeared nearly empty in optical surveys. Spitzer's observations revealed the central bar, an elongated structure of billions of stars stretching across tens of thousands of light-years, previously hidden behind thick clouds of dust. While infrared observations illuminated the inner galaxy, the Gaia mission, launched in 2013, revolutionized our ability to map the Milky Way in 3 dimensions. By precisely measuring the positions, distances, and motions of over 1 billion stars, Gaia provided an unprecedented map of the stellar distribution throughout the disk and halo. These data revealed not only the spiral arms and bar, but also vast stellar streams left behind by disrupted satellite galaxies, echoing the Milky Way's history of cannibalism and growth. Gaia turned the Milky Way from a 2-dimensional mystery into a 3-dimensional living structure, complete with motion, history, and hidden complexities. The spiral arms, the iconic features we often associate with images of galaxies, are not fixed highways of stars. Instead, they are transient density waves, regions where stars, gas, and dust become temporarily concentrated, creating the familiar sweeping patterns. Stars move in and out of these arms over millions of years, like cars passing through a traffic jam. Our Sun, for example, completes an orbit around the galactic center roughly every 225 million years, passing through multiple spiral arms along the way. The arms are not solid structures. They are ephemeral gatherings of matter, maintained by gravitational forces, compressing gas clouds and igniting new generations of stars. These density waves play a crucial role in the galactic ecosystem. As gas enters a spiral arm, it becomes compressed, triggering bursts of star formation. Stellar nurseries emerge, glowing with the brilliant light of young, massive stars. Over time, these stars drift out of the arm, leaving behind clusters, associations, and scattered remnants. In this way, the spiral arms act as both engines and markers of the Milky Way's ongoing evolution, a temporary scaffolding that organizes star formation on vast scales, yet slowly reshapes itself over time. Mapping from within also reveals unexpected distortions and warps. The galactic disk is not a perfectly flat plane. Observations of distant stars show that the outer regions bend and twist, forming a warp that may be caused by gravitational interactions with satellite galaxies like the Large and Small Magellanic Clouds. Even minor tidal forces exerted over billions of years can twist the disk into subtle undulations, further complicating the task of mapping our home. These warps remind us that the Milky Way is not static. It is alive, molded by both internal dynamics and external gravitational influences. The halo, a vast faint sphere of stars and dark matter surrounding the disk, is even more challenging to observe. Halo stars are sparse, and many are relics of smaller galaxies consumed long ago. Their motions trace the gravitational contours of the Milky Way's dark matter halo, a structure that extends far beyond the visible disk. Through careful measurement of these stars, astronomers can infer the mass distribution of the galaxy and gain insight into the invisible scaffolding that holds it together. Gaia's precise data on these distant stars allows us to detect stellar streams, remnants of galactic mergers that occurred billions of years ago, offering a fossil record of the Milky Way's assembly. Interstellar dust, 1c, considered a hindrance, has become a tool in its own right. By observing how dust absorbs and scatters light, astronomers can map its distribution and infer the underlying stellar populations hidden within. Combined with infrared surveys, radio observations of molecular gas, and stellar parallax measurements, this multi-wavelength approach creates a layered, dynamic map of the Milky Way, revealing structures that span from the dense galactic core to the tenuous outer halo. One of the most remarkable revelations from these studies is the complexity of the Milky Way's spiral pattern. Far from a simple set of symmetrical arms, the galaxy exhibits branches, spurs, and asymmetries, reflecting both the transient nature of spiral density waves and the influence of satellite galaxies, massive gas clouds, and gravitational perturbations. The map of the Milky Way is therefore not a static blueprint, but a living, evolving diagram, a structure in constant motion, both orderly and chaotic. The central bar, first revealed clearly by Spitzer and later confirmed by Gaia, plays a pivotal role in shaping the spiral arms. Its gravitational influence channels gas inward, feeding star formation in the inner regions and possibly fueling the activity around Sagittarius A. The bar rotates faster than the stars in the disk, creating a dynamic interaction that compresses gas, triggers star formation, and influences the motion of stars across the inner galaxy. In essence, the bar is both a structural backbone and a dynamic engine, shaping the flow of matter and energy in the Milky Way. Even with all these technological advances, mapping the Milky Way remains an ongoing challenge. Our position within the disk, the warping of outer regions, the obscuring dust, and the sheer scale of the galaxy make every observation a partial view. Yet, piece by piece, astronomers have begun to assemble a coherent picture, integrating data from multiple missions, wavelengths, and techniques. This map is not merely a catalog of stars. It is a story of motion, evolution, and cosmic history, a record of where we are and how we got here. The insights gained from mapping the Milky Way extend beyond cartography. They reveal the processes that sustain the galaxy, the birth of stars, the recycling of gas and dust, the growth of stellar clusters, and the remnants of galaxies long consumed. Each arm, cluster, and stream is a chapter in the Milky Way's biography, a testament to billions of years of cosmic evolution. Our place within this structure is fleeting, yet it allows us to witness the unfolding of processes on scales that dwarf human experience. By understanding the Milky Way's architecture, we also gain perspective on our cosmic insignificance and connectedness. The Sun is one star among hundreds of billions, orbiting within a spiral arm, tracing paths carved by gravitational waves, density patterns, and stellar motion. Our planet, our life, our history, all unfold on a tiny stage within a vast dynamic system. Mapping the galaxy reminds us that the story of the Milky Way is ongoing, and our brief existence is part of a much grander narrative. From this vantage point, one question emerges. How do these structures, spiral arms, bars, warps, and halos, interact with the galaxy's unseen components? Beyond the stars and gas lies dark matter, stretching the Milky Way's gravitational influence far beyond what we can see. How do these visible features trace the contours of the eye, invisible scaffolding that holds the galaxy together? Mapping the galaxy is therefore not just a visual exercise. It is an exploration of hidden forces and cosmic architecture. A detective story unfolding across tens of thousands of light years. As we piece together the Milky Way from within, we glimpse a universe that is simultaneously familiar and alien. Every arm, star cluster, and dust lane has its place in a complex, interwoven tapestry. And yet, from our position inside the galaxy, we cannot step back to view the whole. We rely on clues, inference, and imagination, combining precision data with cosmic storytelling to create a picture that captures both the structure and the spirit of our home. The Milky Way, as revealed through Gaia, Spitzer, and modern surveys, is not a static monument, but a living city of stars, a dynamic system shaped by gravity, motion, and time. Its spiral arms are not permanent avenues, but fleeting gatherings. Its central bar channels gas and organizes motion. Its halo bears the signatures of cannibalized galaxies. To map the Milky Way is to trace the invisible threads that bind stars, gas, and dark matter, to follow the currents that guide matter across hundreds of thousands of light years, and to understand the hidden choreography of a galaxy in motion. Cosmic predators, in the quiet darkness of space, a silent drama unfolds. Our galaxy, the Milky Way, is not a passive observer in the cosmos. It is a predator, patient and relentless, shaping its destiny by consuming the smaller galaxies that wander too close. This process, known as galactic cannibalism, has been a fundamental mechanism of growth for galaxies across cosmic history, and our own stellar home is no exception. Consider the Sagittarius dwarf elliptical galaxy, a small collection of roughly 4 billion stars, insignificant by galactic standards, yet caught in a gravitational trap. As it drifts into the Milky Way's domain, the Sagittarius dwarf is stretched and torn apart by tidal forces, its stars stripped from the core and flung across the galaxy. Vast stellar streams, some forming arcs tens of thousands of light years long, trace its orbital path, like ribbons marking the route of a once cohesive entity, now unraveling under our galaxy's immense gravity. Each passage through the Milky Way's dense disk further erodes the dwarf, shrinking its size and scattering its stars into the larger galactic population. Simulations suggest that in a few billion years, the Sagittarius dwarf will vanish entirely, leaving only these streams as evidence of its existence. But the Sagittarius dwarf is just one example. Even our largest nearby satellites, the Large and Small Magellanic Clouds, are destined for eventual disruption. These dwarf irregular galaxies, visible to the naked eye from the southern hemisphere, may not be stable companions at all. Current measurements of their motion indicate they could be making their first close approach to the Milky Way, newly captured by our gravitational influence. Over billions of years, tidal forces will strip their stars and gas, feeding the Milky Way's spiral arms and triggering fresh bursts of star formation. In this way, ruction begets creation, as the death throes of one galaxy become the seeds for new stellar life in another. Even the smallest galaxies are not immune. Ultra-faint dwarf galaxies, containing only a few thousand stars, bear the scars of past interactions. Their elongated shapes and disturbed stellar distributions are testimony to the gravitational violence they have endured. These diminutive companions reveal that galactic predation is not reserved for the grandest structures. It is a fundamental aspect of cosmic evolution, affecting galaxies of all sizes and ages. But how do we know this is happening? The evidence lies in the motions and distributions of stars throughout the Milky Way. Surveys such as Gaia have mapped stellar streams with exquisite precision, revealing patterns too regular to be coincidental. These streams are the remnants of long-dead galaxies, their stars now woven into the fabric of the Milky Way, contributing to the smooth halo that envelops our spiral disk. Many of the stars in this halo were not born here. They are the recycled remains of ancient satellites, captured and integrated over billions of years. The process of galactic cannibalism operates on scales that are almost unimaginable. A single orbit around the Milky Way takes hundreds of millions of years, and the gradual erosion of a dwarf galaxy can take billions. Yet, over these immense timescales, our galaxy accumulates mass, grows in size, and reshapes its structure. Large galaxies like ours expand not by drawing in diffuse intergalactic gas alone, but primarily by devouring smaller neighbors, incorporating their stars, gas, and dark matter into an ever-evolving whole. One of the most striking consequences of this process is the formation of stellar streams. When a dwarf galaxy is torn apart, its stars are not immediately scattered randomly. Instead, they follow the orbital path of their former home, forming elongated streams that wrap around the Milky Way. Some of these streams stretch across the entire sky, invisible to the naked eye, but detectable through precise astrometry and spectroscopy. By studying these streams, astronomers can reconstruct the original orbit, mass, and composition of the disrupted galaxy, effectively reading the fossil record of the Milky Way's growth. This ongoing construction is not limited to stars alone. Gas stripped from satellite galaxies contributes to the Milky Way's interstellar medium, replenishing the material necessary for new generations of star formation. Clouds of hydrogen and heavier elements from these smaller galaxies settle into the spiral arms, where compression waves trigger the birth of new stars. In this sense, the Milky Way is both predator and gardener, harvesting the remains of smaller systems to cultivate fresh stellar life. Galactic cannibalism also reveals the dynamic nature of cosmic architecture. The Milky Way is not a static spiral frozen in time. It is a living, breathing system, continually shaped by interactions with its surroundings. Each dwarf galaxy captured, each tidal stream formed, subtly alters the gravitational landscape. Spiral arms shift, bars rotate, and the halo evolves, reflecting the ongoing influence of these cosmic encounters. Even the motions of our sun and neighboring stars are affected, tracing paths influenced by the integrated mass of these absorbed companions. The Large Magellanic Cloud, for example, is already pulling on the Milky Way, creating distortions in the halo and disk. Its gravity perturbs the orbits of stars and globular clusters, while its gas contributes to new star formation along the spiral arms. Over billions of years, the LMC may merge fully with the Milky Way, leaving only streams of stars and subtle gravitational signatures as a testament to its former identity. Beyond our immediate neighborhood, The same patterns are evident throughout the universe. Observations of other spiral galaxies reveal streams, shells, and disrupted satellites, confirming that galactic cannibalism is a universal mechanism. Our galaxy is part of a broader pattern, one in which large structures grow through accumulation, constantly reshaping themselves through collisions, mergers, and tidal interactions. It is a universe in motion, a cosmos where creation and destruction are intertwined in an eternal cycle. Even more dramatic is the role of dark matter in this cosmic predation. Each galaxy is embedded in a massive dark matter halo, extending far beyond the visible stars. These halos dominate the gravitational potential, guiding the paths of satellites and influencing how they are stripped and absorbed. Without dark matter, the delicate dance of tidal disruption would be less orderly, and many smaller galaxies might escape, rather than succumb to the Milky Way's pull. Dark matter acts as the unseen stage upon which these cosmic dramas unfold, shaping the orbits and fates of countless stars. As we map these processes, a deeper truth emerges. The Milky Way is both old and ever-changing. Its current form is the product of billions of years of cosmic predation. Yet this evolution is far from complete. New dwarf galaxies continue to fall into our domain, while the streams of past mergers crisscross the halo like invisible scars. The galaxy we inhabit is a mosaic of ancient survivors, recycled stars, and freshly formed regions, a structure constantly in flux, constructed from the remains of countless others. The implications of this cannibalistic growth extend beyond astrophysics. They remind us of the scale and timescales of the cosmos. Individual stars, planetary systems, and even civilizations are but fleeting moments in a universe that operates on billions of years. The Milky Way itself is both predator and prey, bound by gravity and shaped by interactions too slow and vast for the human mind to fully grasp. Yet through careful observation and patient inference, we can reconstruct these stories, piece together the galaxy's history, and glimpse the forces that have shaped our cosmic neighborhood. Galactic cannibalism also underscores the interconnectedness of the universe. No galaxy exists in isolation. Each is influenced by companions, satellites, and the surrounding cosmic web. The Milky Way's history is entwined with the fates of countless smaller systems, and in turn, our galaxy will eventually collide with Andromeda, the nearest spiral of comparable size. The ongoing process of growth through absorption, which we observe in the Sagittarius dwarf and Magellanic clouds, foreshadows an even grander future collision, a cosmic merging that will reshape both galaxies over billions of years. Through the study of tidal streams, disrupted satellites, and galactic halos, astronomers have begun to read the Milky Way's autobiography. Each stream is a sentence, each absorbed galaxy a chapter. The story is long, stretching across billions of years, and it is still being written. By observing the motions of stars, measuring the composition of stellar populations, and mapping the halo's structure, we trace the echoes of ancient encounters and witness the galaxy's construction in real time. Even from our vantage point, within the disk, the evidence is unmistakable. The halo is a patchwork, stitched together from hundreds of smaller galaxies consumed over the Milky Way's lifetime. These stars are not random. They carry the chemical fingerprints of their origins, allowing astronomers to distinguish which dwarf galaxy they came from. Through this cosmic archaeology, we gain insight into both the galaxy's past and the broader processes that govern galaxy formation throughout the universe. Galactic cannibalism is not a violent frenzy, but a slow, inexorable process. Over billions of years, gravitational forces tear, stretch, and redistribute stars, quietly reshaping the Milky Way. In this sense, the galaxy is both predator and archivist, preserving the memory of its victims even as it consumes them. Each tidal stream is a fossil, each disrupted dwarf a witness to the Milky Way's relentless growth. And yet, for all its scale, this process mirrors life in miniature. Creation and destruction, growth through absorption, and evolution shaped by interaction. These are themes that resonate across both cosmic and terrestrial realms. The Milky Way teaches us that even on the grandest scales, nothing is fixed. Everything is in motion, and the past is written into the structures that surround us, the bar and the arms. Hidden within the glow of countless stars lies a structure so vast, so central to the identity of our galaxy, that it has remained invisible to human eyes for millennia. From our vantage point, deep within one of the Milky Way's spiral arms, the galaxy appears as a hazy ribbon of light stretching across the night sky. Yet the true architecture of this cosmic city was obscured, masked by dense clouds of dust, tangled gas, and the sheer scale of the system itself. It wasn't until the advent of infrared astronomy and precision astrometry that we began to unravel one of the Milky Way's most defining features, its central bar. This elongated cluster of billions of stars stretches roughly 27,000 light-years from end to end, cutting across the galactic center like the handle of a cosmic dumbbell. Far from being a static ornament, the bar is a dynamic, rotating structure that drives much of the Milky Way's internal motion. But what purpose does this stellar engine serve, and why does it matter for the ongoing evolution of our galaxy? The central bar functions as a conveyor belt of cosmic matter. Its gravitational influence channels gas from the outer regions inward, funneling raw material toward the central bulge and the supermassive black hole lurking at the galaxy's heart. Here, gas clouds spiral inward, compressed and heated as they approach the core, feeding the black hole in periodic bursts of activity. These feeding events are not mere curiosities. They shape the surrounding galactic environment, triggering high-energy radiation and influencing the formation of nearby stars. In essence, the bar is both a cosmic engine and a cosmic sculptor, shaping the flow of matter, energy, and light within the Milky Way. Beyond the central bulge, the bar also orchestrates the spiral arms, the grand patterns of stars, gas, and dust that define the Milky Way's conic shape. These arms are not rigid structures, but transient traffic jams of stars and interstellar matter, compressed along waves of gravitational perturbation. As the bar rotates, it generates density waves that ripple outward through the disk. Gas clouds caught in these waves are squeezed to higher densities, igniting new bursts of star formation. The arms themselves are alive with activity. Stellar nurseries glow brightly with young, massive stars, while pockets of interstellar gas collapse into protostars, destined to ignite in nuclear fusion. Star formation is a cycle of creation and destruction, intimately linked to the bar and arms. Massive stars burn their fuel with astonishing speed, living only a few million years before exploding as supernovas. These explosions are both catastrophic and creative. Shock waves compress surrounding gas, triggering new rounds of star formation, while the stellar remnants, neutron stars and black holes, become silent witnesses to the galaxy's ongoing evolution. Meanwhile, lower mass stars like our Sun burn steadily for billions of years, providing stable environments where planetary systems can form and potentially life can emerge. Every generation of stars contributes to the chemical enrichment of the galaxy. The earliest stars, forged from nearly pure hydrogen and helium, lacked the heavier elements necessary for rocky planets or biological chemistry. When these primordial stars died, they seeded the interstellar medium with carbon, oxygen, silicon, and iron, elements forged in the crucibles of their cores. Subsequent generations incorporated these heavier elements, gradually enriching the galaxy's material and enabling the formation of planets like Earth. Our Sun itself, a third-generation star, is a product of this cosmic recycling, containing in its composition the echoes of countless stellar deaths. The bar's rotation also influences the timing and location of star formation. Unlike the steady orbit of our Sun around the galactic center, the bar rotates faster than the stars in the disk. This creates resonances where different parts of the galaxy periodically align with the bar's gravitational influence. When these alignments occur, waves of star formation propagate outward along the spiral arms, producing stellar fireworks visible across thousands of light years. In this way, the galaxy is not a static collection of stars, but a rhythmic, almost musical system, with patterns of creation playing out over cosmic time. Yet even as the bar channels gas inward, it gradually loses angular momentum to the surrounding disk, growing longer and more prominent over billions of years. This slow evolution has implications for the Milky Way's future. As the bar strengthens, it may trigger new bursts of star formation in the central regions, alter the spiral pattern, and even influence the orbits of stars in the inner disk. It is a reminder that the galaxy is a living structure, continuously reshaping itself under the influence of internal dynamics and the remnants of past encounters. Observations from the Spitzer Space Telescope and the Gaia mission have been instrumental in uncovering these hidden dynamics. Infrared light penetrates the dust that obscures our view, revealing the distribution of stars deep in the galactic center. Gaia's precise measurements of stellar positions and motions allow astronomers to map the bar's rotation and the flow of stars along the arms with unprecedented accuracy. Together, these missions have transformed our understanding of the Milky Way from a vague, hazy band to a complex, interconnected system with dynamic structures and ongoing cycles of birth and death. The bar also provides a gravitational anchor for the galaxy. Without it, the disk would lack the coherence necessary to sustain spiral arms, and star formation would proceed in a more chaotic, scattered manner. Its presence stabilizes the inner regions, creating resonances that organize stars and gas, guiding them along predictable paths. Even stars hundreds of light years from the center are subtly influenced by the bar's gravity, tracing arcs and ripples that reflect the unseen hand shaping the galaxy from within. Chemical enrichment from multiple stellar generations ensures that the spiral arms are not only visually striking but chemically diverse. Stars born in different epochs carry distinct elemental fingerprints, allowing astronomers to trace the history of star formation across the disk. Regions enriched by past supernovas are more likely to produce planets with the raw materials for life, linking the galaxy's structural dynamics to the potential for biological evolution. Every star, every cluster, every burst of formation is a note in a cosmic symphony, echoing billions of years of growth, decay, and renewal. Yet for all its beauty and complexity, the Milky Way is a fragile choreography of gravitational interactions. The bar, the spiral arms, and the central bulge exist in delicate balance, influenced not only by internal dynamics, but also by interactions with satellite galaxies and the broader cosmic environment. The large and small Magellanic Clouds tug on the disk, subtly warping its outer regions. Streams of stars from disrupted dwarfs ripple through the halo, creating patterns that resonate with the bar's own gravitational waves. The galaxy is a network of cause and effect, where the smallest perturbation can have consequences felt tens of thousands of light-years away. This intricate interplay reminds us of the scale of time and space over which the Milky Way operates. The bar rotates over hundreds of millions of years. Spiral arms shift and fade over similar intervals, and chemical enrichment unfolds over multiple stellar generations. Human lifetimes, by contrast, are mere flickers, instants in the cosmic clock. Yet, through careful observation, simulation, and deduction, we can witness the rhythm of the galaxy, decoding its history and anticipating its future. By understanding the bar and the spiral arms, we gain insight into how galaxies like the Milky Way sustain themselves. Star formation is not random. It is guided, orchestrated, and amplified by these structures. The bar feeds the core, the arms channel material outward, and supernovas recycle matter back into the interstellar medium. Over billions of years, this self-sustaining cycle transforms primordial hydrogen into stars, planets, and the chemical building blocks of life itself. And yet, despite this complexity, the Milky Way remains typical in many respects. Spiral galaxies with central bars are among the most common structures in the universe. Roughly 2/3 of spiral galaxies exhibit similar patterns, with bars and arms driving internal dynamics. What makes our galaxy extraordinary is not its uniqueness, but the detail and clarity with which we can observe it, mapping not just the stars themselves, but the invisible flows of matter, the chemical fingerprints of multiple generations, and the subtle gravitational currents sculpting the disk. From our vantage point within the solar system, we see only fragments: the glowing patch of the Milky Way across the night sky, clusters of young stars, and nebulae glowing in scattered clouds of gas. Yet when we step back, mentally or through simulation, we perceive the full choreography: the rotating bar, the spiraling arms, key dynamic cycles of star birth and death. It is a system of astonishing scale, elegance, and subtlety, a testament to the forces of gravity, gas dynamics, and time acting over billions of years. Dark matter and the galactic halo. Beyond the bright, glittering disk of our galaxy lies a realm largely invisible to human eyes, a shadowy, enigmatic domain that defines the true scale and structure of the Milky Way. This is the galactic halo, an extended sphere of stars, gas, and most intriguingly, dark matter, stretching nearly 2 million light-years from the galactic center. To put this in perspective, the familiar spiral arms of the Milky Way span roughly 100,000 light-years. The halo, by contrast, envelops everything we see, and then some, reaching nearly 20 times farther than the visible stars. Unlike the stars and glowing gas that light up our night sky, dark matter cannot be seen, touched, or measured directly. It neither emits nor absorbs light. Yet its presence is undeniable. Astronomers infer it from the gravitational influence it exerts on the visible galaxy, the motion of stars in the outer disk, the orbits of satellite galaxies, and the bending of light from distant objects all point to a vast, invisible mass, far outweighing the stars themselves. The Milky Way, it seems, is but a luminous pearl, floating within an ocean of unseen matter. This dark matter halo is more than a passive cloak. It is the scaffolding upon which our galaxy is built. Without it, the spiral disk would not remain stable. Satellite galaxies would not follow their measured paths, and the Milky Way itself could not have formed into the graceful spiral we inhabit today. Every star, every cluster, and every tidal stream traces its motion along the gravitational contours defined by this invisible halo. The halo dictates the cosmic choreography, determining which satellites are captured, which are torn apart, and which might escape entirely. Embedded within this halo are the remnants of ancient galactic interactions. Stellar streams, formed from tidally disrupted dwarf galaxies, arc through the halo like silver threads, silently recording past encounters. Each elongated ribbon of stars tells a story of cosmic predation. A small galaxy drawn too close, stretched by gravitational tides, and gradually disassembled into its constituent stars. The halo is a graveyard and a library, preserving the Milky Way's history across billions of years. Yet stars and stellar debris are only part of the picture. The halo is suffused with magnetic fields, invisible lines of force stretching across vast distances. Though thousands of times weaker than a refrigerator magnet, these fields extend across the galaxy, threading through the disk and halo alike. They act as cosmic highways, guiding charged particles, shaping the motion of interstellar gas, and subtly influencing where stars can form. High-energy protons and electrons spiral along these magnetic tracks, traveling tens of thousands of light years before encountering obstacles that deflect their paths. The magnetic web is like a hidden skeleton, invisible, yet fundamentally shaping the behavior of matter across the galaxy. These fields are born from the motion of electrically conducting gas. As clouds of ionized hydrogen swirl within the galaxy, they generate currents that produce magnetic fields. The rotation of the Milky Way stretches and twists these fields into the large-scale spiral patterns we now observe. Compressions, tangles, and reconnections release bursts of energy, influencing local star formation, and sometimes even producing cosmic fireworks observable across interstellar distances. In this way, magnetic fields act as both guides and regulators, subtly steering the birth and death of stars, while remaining largely invisible to our senses. The halo and its magnetic highways also govern the orbits of satellite galaxies. The large and small Magellanic Clouds, along with dozens of smaller companions, travel along paths determined by the combined gravitational influence of the halo and the central disk. As they swing through the galaxy, tidal forces strip stars and gas, adding to the halo's stellar population. Over billions of years, these interactions feed the Milky Way's growth, both by increasing its mass and by injecting fresh material that will eventually form new generations of stars. But the halo is not static. It is a dynamic, ever-changing environment. Dark matter interacts gravitationally with itself and with visible matter, creating subtle waves and clumps that ripple through the galaxy. These fluctuations influence the orbits of stars, trigger new rounds of star formation, and may even affect the spiral pattern of the disk. In essence, the halo acts as a vast invisible hand, shaping the Milky Way's evolution while remaining entirely unseen. Despite its invisibility, we can map the halo's influence. Observations from missions like Gaia have measured the motions of distant stars and satellite galaxies with exquisite precision, revealing the halo's shape and extent. The distribution of stellar streams, the velocities of outer disk stars, and the gravitational lensing of background galaxies all provide clues to the halo's mass and structure. These studies reveal that the Milky Way is not an isolated island, but a node within a cosmic web, its dark matter halo bridging the space between galaxies and interacting with the halos of neighbors like Andromeda. In fact, the dark matter halos of our galaxy and Andromeda may already be overlapping, foreshadowing the grand collision that will occur billions of years from now. Within this halo, star formation continues, albeit at lower rates than in the dense disk. Gas, drawn from tidal interactions or accreted along cosmic filaments, can cool and collapse to form new stars, adding fresh light to the galaxy's outskirts. Even far from the bustling spiral arms, the halo acts as a reservoir of material, supporting the galaxy's long-term evolution. It is a subtle but persistent engine of creation, quietly shaping the Milky Way's destiny over billions of years. The halo's vast scale also offers perspective on our cosmic position. From Earth, we see only the disk's bright stars and nebulae, a thin slice of the galaxy's total mass. Beyond the visible edge lies a nearly empty-looking void, but in reality, it is filled with dark matter, tenuous gas, and scattered stars. Our sense of the galaxy's size expands by orders of magnitude once we account for the halo, revealing a structure that stretches nearly halfway to our nearest massive neighbor, Andromeda. We are far from the center, yet even here, we feel the gravitational pull of this immense, invisible halo. And yet, for all its mystery, the halo is intimately tied to the galaxy we inhabit daily. Its gravitational pull determines the solar system's orbit around the galactic center, keeps the disk from tearing apart, and guides the motion of countless stars that form the background of our night sky. The halo is a quiet architect, operating behind the scenes to maintain the delicate balance that allows the Milky Way to persist as a coherent, functioning galaxy. Even more remarkably, the halo connects the Milky Way to the largest structures in the universe. Filaments of dark matter stretch across intergalactic space, linking galaxy clusters and guiding the flow of matter. Gas can funnel along these filaments, feeding galaxies like ours, while the gravitational pull of dark matter shapes the motion of satellites and the orbits of neighboring systems. In this sense, the halo is both local and cosmic, a bridge between our familiar galactic environment and the vast interconnected cosmic web. In contemplating the halo, we confront one of astronomy's most profound mysteries, the invisible framework of the universe. Most of the matter in the Milky Way, and indeed most of the matter in the universe, is unseen, detectable only through its gravitational imprint. This hidden mass shapes galaxies, governs interactions, and dictates the ultimate fate of stars and planets alike. It reminds us that what we see, the stars, the nebulae, the spiral arms, is only a fraction of the galaxy's true reality. The rest remains concealed, a silent influence spanning millions of light years. Through observation, simulation, and inference, we begin to map this invisible world, tracing the outlines of the halo, the flows of magnetic highways, and the gravitational paths of satellite galaxies. We gain not only a sense of scale, but also an understanding of the forces that govern cosmic evolution. In the halo, the Milky Way reveals itself as both fragile and resilient, shaped by unseen matter, yet enduring across billions of years. The cosmic web. If we think of the Milky Way as a solitary city in the night, shimmering with billions of lights, the truth is far more astonishing. Our galaxy is not isolated. It is part of a vast, intricate tapestry that stretches across the universe, a cosmic web connecting galaxies, clusters, and superclusters in a delicate, invisible framework. In this web, galaxies are not scattered randomly, but are strung along filaments of matter, tracing paths carved by gravity over billions of years. To imagine this scale is to confront the almost incomprehensible vastness of the cosmos. The Milky Way sits within one of these filaments, a long, narrow strand of matter stretching across millions of light years. These filaments are composed of both dark matter and ordinary matter, the latter forming galaxies, clusters, and the tenuous intergalactic medium. Along these strands, galaxies travel like boats on a river, carried inexorably by the gravitational currents created in the universe's infancy. The paths they follow are determined by the hidden skeleton of dark matter, a framework invisible to our eyes, yet omnipresent across cosmic scales. Our local neighborhood, the local group, which includes the Milky Way, Andromeda, and roughly 50 smaller galaxies, is not adrift in emptiness. It is embedded within a filament that stretches toward the Virgo cluster, a massive collection of over 1,300 galaxies located roughly 54 million light-years away. The gravitational pull of this cluster, along with other massive structures, subtly guides the motion of our galaxy, creating a steady drift through space that spans millions of light-years. Even though this motion is imperceptible on human timescales, over cosmic history, it defines the journey of our galaxy through the universe. Gravity, in this context, behaves as a cosmic river, flowing along the contours of the dark matter web. Each galaxy is a passenger on this river, moving along paths determined not by chance, but by the mass distribution of surrounding structures. Some galaxies collide, merge, or are captured along the way, while others travel relatively untouched for billions of years. These flows of matter are not chaotic. They follow patterns etched into the universe itself by the subtle amplification of tiny fluctuations in the primordial density of the cosmos. One of the most profound structures along this cosmic web is the Great Attractor, a gravitational anomaly lying tens of millions of light-years away. Though hidden behind the plane of the Milky Way, its influence is unmistakable. Observations of galactic motions reveal that our local group, along with hundreds of thousands of neighboring galaxies, is being drawn toward this unseen concentration of mass. The Great Attractor is not alone. It is part of an even larger structure, the Shapley supercluster, containing thousands of galaxies and immense reservoirs of dark matter. These colossal assemblies define the ultimate destinations of the gravitational currents that guide our galaxy's motion. But gravity is only part of the story. Between the galaxies lies the intergalactic medium, a vast, diffuse soup of hot ionized gas spread across the voids of space. Though nearly invisible, this medium contains significant mass and plays a critical role in galaxy formation and evolution. Gas flows along the filaments of the cosmic web, feeding galaxies like ours and providing the raw material for star formation. In a sense, the cosmic web is both a river and a reservoir, guiding the motion of galaxies while delivering the building blocks of stars, planets, and ultimately, life. The filaments themselves are not uniform. They twist and curve, connecting dense clusters with long stretches of emptiness. These voids, enormous regions containing very little matter, act as the negative spaces of the cosmic tapestry. Galaxies skirt these voids, traveling along the paths of least resistance defined by gravity and dark matter. From our perspective, it is as if the universe is a vast spiderweb with luminous nodes connected by invisible threads, each galaxy riding along its own strand. The cosmic web also gives context to the motions within the Milky Way. While we often consider our galaxy as spinning gracefully in isolation, its trajectory is part of a far larger flow. The orbit of the Milky Way around the local group's center of mass, its eventual collision with Andromeda billions of years from now, and the countless encounters with satellite galaxies. All of these events are shaped by the galaxy's position within this larger cosmic framework. In this way, our galactic home is both local and cosmically connected, its destiny intertwined with structures millions of light-years away. Even more remarkably, the web is self-organizing, emerging naturally from the earliest fluctuations in the universe. After the Big Bang, tiny variations in density caused matter to clump and stretch under the force of gravity. Over billions of years, These clumps form the nodes, filaments, and voids we see today. Computer simulations show that these structures arise inevitably, producing the vast network that guides galaxies through the cosmos. In this sense, the Milky Way's position in the web is not random. It is the result of a cosmic architecture written into the fabric of space itself. The cosmic web also affects the chemical evolution of galaxies. Gas streaming along filaments brings fresh material into galaxies, replenishing what is consumed by star formation. Collisions and mergers along these paths stir the interstellar medium, triggering bursts of star formation and mixing the elements produced in previous generations of stars. In this way, the web acts as both conveyor and catalyst, shaping the evolution of galaxies over billions of years. Gravity's influence on the cosmic web is subtle but persistent. The Milky Way does not drift aimlessly. It follows a predetermined course, guided by massive concentrations of matter, both visible and invisible. Over billions of years, these currents have carried our galaxy from one cosmic neighborhood to another, shaping its encounters, mergers, and growth. The flows of galaxies along the web illustrate a fundamental truth. The universe is highly structured, its apparent chaos hiding an underlying order that governs even the motion of entire galaxies. Through observational astronomy, we are beginning to map this vast network. Surveys detecting galaxy distributions, gravitational lensing, and X-ray emission from hot gas reveal the shape and connectivity of the filaments. Each discovery expands our understanding, showing that our galaxy is but one luminous node in an almost unfathomable web of matter. The Milky Way's journey is both unique and ordinary, an example of the countless galactic paths traced along these filaments throughout the universe. Yet the cosmic web is not static. The motions of galaxies, the accretion of gas, and the slow merging of clusters continuously reshape the network. The flows of matter along filaments feed not just galaxies, but also larger-scale structures like superclusters and massive voids. Over cosmic time, this intricate web evolves, stretching, bending, and reconnecting in a process as slow and grand as the age of the universe itself. From our vantage point within the Milky Way, we cannot see the web directly. We perceive only the immediate surroundings, the stars of our galaxy, and the faint light of neighboring galaxies. But by piecing together observations across vast distances, astronomers have reconstructed the invisible architecture that governs our motion. The Milky Way is not drifting randomly through emptiness. It is a vessel carried along the streams of the cosmic web, guided by the gravity of structures far beyond our imagination. And yet, despite this immensity, the web is intimate in its influence. The Milky Way's history and future, from the capture of satellite galaxies to the formation of new stars, from the enrichment of chemical elements to the eventual collision with Andromeda, are all connected to this network. In a very real sense, we are riding on a river of gravity, bound by the currents of dark matter and the structure of the cosmos itself. The cosmic web also challenges our sense of scale. The Milky Way, immense as it seems, is but a single thread in a tapestry containing trillions of galaxies. Superclusters like Shapley or Virgo are mere knots along this network, with filaments stretching tens of millions of light-years between them. The flows of matter along these filaments remind us that the universe is dynamic, with galaxies moving, interacting, and evolving in concert with the hidden scaffolding around them. Finally, the cosmic web is a testament to the interconnectedness of the universe. The Milky Way is a luminous island in a vast, flowing network, influenced by distant clusters, shaped by invisible matter, and fed by intergalactic rivers of gas. Our galaxy's journey through space is a story written across billions of light-years, a narrative of motion, gravity, and cosmic architecture that far exceeds the scope of human experience. Citizens of infinity, imagine for a moment that you could step outside the Milky Way, not metaphorically, but truly lift yourself above the galactic disk, far beyond the reach of our light years, and gaze upon our home from an impossible vantage point. What would you see? You would behold a luminous spiral, a galaxy of 400 billion stars arranged in elegant arms that coil outward from a brilliant central bulge. Blue-white clusters of young stars would sparkle along the spiral arcs, while older yellow stars would fill the spaces between with a warm, steady glow. Dark lanes of cosmic dust would lace the spiral arms, tracing intricate patterns of shadow and light, like the delicate brushstrokes of an unseen artist. From this distance, the central bar stretching across the heart of our galaxy would be unmistakable. Its elongated shape, containing billions of stars, rotates slowly around the supermassive black hole at the core, orchestrating the movements of gas and stars alike. Surrounding the disk, the halo of ancient globular clusters would appear as tiny jewels scattered across the darkness, each a testament to the earliest epochs of our galaxy's formation. And yet, the halo and the disk together would reveal only a fraction of the Milky Way's full reach. Its invisible dark matter halo, stretching nearly 2 million light-years, would remain hidden, detectable only through its gravitational influence, a ghostly presence that binds together all that is visible. Even from this impossible perspective, the Milky Way would not exist in solitude. Streams of stars torn from smaller, disrupted galaxies would trace delicate arcs around the disk, reminders of countless cosmic encounters and galactic cannibalism that have shaped our home. Farther away, the approaching Andromeda galaxy would loom like a neighboring metropolis, its own spiral arms and halo gradually drawn. From this vantage, time takes on a different meaning. The spiral arms, the bar, the globular clusters, even the dark matter halo, none of it is permanent. Stars are born, live and die, tidal streams drift outward, black holes consume gas and stars, and galaxies themselves merge and reshape over billions of years. Our human lifespan, fleeting in comparison, becomes almost incomprehensible when measured against these cosmic cycles. Every atom in our bodies, every molecule that carries the signature of life on Earth, has been forged through these cycles of stellar birth and death. We are the products of time, motion, and matter that span scales far beyond our comprehension. Yet for all its immensity, the universe is intelligible. We can trace our position along filaments of the cosmic web, observe the slow flow of galaxies toward massive clusters, and map the orbits of stars within our galaxy. We can identify the streams of stars left behind by devoured satellites, measure the rotation of the central bar, and even detect the faint whispers of magnetic fields threading through interstellar space. Humanity is not merely a passive observer. In piecing together this cosmic story, we have become chroniclers of the universe itself, decoding the history of billions of years from the light of distant stars. Our place within this structure is both insignificant and profound. Insignificant, because the Milky Way itself is one among trillions of galaxies, each containing billions of stars. The sheer scale of the cosmos renders any individual life infinitesimal, a flicker against the backdrop of cosmic eternity. Yet our ability to observe, understand, and reflect grants us a kind of significance that transcends scale. We are conscious citizens of infinity, capable of perceiving the grandeur around us and of contemplating the forces that shape it. In that sense, we are both infinite. From our vantage point inside the Milky Way, we cannot step outside to see the whole galaxy. We are trapped within our cosmic cathedral, able to examine individual elements but never the totality of its design. Yet through ingenuity, observation, and imagination, we reconstruct the galaxy piece by piece. We chart the spiral arms, map the stellar streams, measure the motion of stars, and simulate galactic evolution. Each discovery deepens our understanding and appreciation, revealing a universe of exquisite complexity, governed by forces both subtle and immense. Even as we map our galaxy, we are connected to the broader cosmos. The Milky Way travels along a filament of the cosmic web, moving toward massive structures like the Virgo cluster and the Shapley supercluster. Its journey is dictated by the invisible currents of gravity, which shepherd galaxies along predetermined paths while allowing for collisions, mergers, and the flow of matter. The galaxy's interactions with its environment shape its evolution just as much as the stars within it, reminding us that nothing exists in isolation. Ultimately, contemplating our place in the Milky Way is a lesson in humility and awe. We are small yet capable of extraordinary insight. We are fleeting yet witness to events that span billions of years. We are temporary passengers on a cosmic river that has carried our galaxy from one corner of the universe to another, a river guided by unseen forces, yet full of beauty, order, and mystery. Our story is far from over. As the Milky Way evolves, as Andromeda approaches, as stars are born and die, we will continue to observe, to question, and to seek understanding. The universe offers no final answers, only deeper mysteries, and our journey as citizens of infinity is to explore, to marvel, and to learn. The cosmos stretches on in all directions, an endless canvas of light, motion, and matter, and within it, we find both our fragility and our capacity for wonder. In the end, the Milky Way is more than a galaxy. It is a living chronicle of time, a stage for the cycles of matter and energy, and a home for conscious observers capable of reflecting on its grandeur. We are its children, its storytellers, and its witnesses, forever bound to its motion, its rhythms, and its infinite horizons. And so we remain, gazing upward, piecing together the fragments of a galaxy we can never fully escape, yet striving always to understand, forever citizens of infinity.